and this thing. All right. Well, thanks for the invitation to come and speak to you today. I'll get to my talk. I wanted to show one slide inspired by the journalist's talk earlier this morning. My night job is as an aspiring journalist in looking into intrigue and accusations of fraud. I've been researching for about a year now fake university presences online, like this particular university here. University, you see the air quotes there, and their relationship, which I think has been relatively underexplored up to this point, with predatory journals, where sometimes some nefarious folks are creating these online presences for fictitious universities, populating them with faculty that look legit, and then those faculty's names end up appearing in the editorial boards of for-profit predatory journals. So that's all I'll say about that. If you're interested in that story, I love telling it, so just talk to me sometime. But that's not what I was invited to talk to you about today. What I'm talking to you about today is looking at a piece of the security, the detection of errors or attacks, but of a particular part of how we control microfluidic chips, in particular valved microfluidic chips. You know, microfluidic valves, there's a few competing kind of technologies out there for them, but generally all of them, most of them are actuated pneumatically, and the on-chip valves, and so the control system for those looks a lot like this. This was a picture I took in my lab, and what you're seeing here is some electronics, some solenoid valves, and some pneumatic pipes here connecting to a little microfluidic chip. And so in general, if you look at it, and that's a very common picture in a lot of labs that do microfluidics. So if you look at a lot of these, you start to see this sort of trend to it, which I tried to summarize here. There's electronic bits that are the computer running my LabVIEW program that has a big old wire that controls a bunch of switches that have a lot of individual wires that switch solenoid valves. And then the solenoid valves here, I tried to color them funny there to show they're sort of the transducer. They're the intermediary between the electronic world and the pneumatic world. And then everything downstream of that is actually pneumatic in a lot of these valved microfluidic chips. So we have tubing, in this case, connected to microfluidic chips which have channels etched into them which connect to the on-chip microfluidic valves that are actually doing the chemistry or the biology of our biochip, okay? And so looking at this got us thinking, these valve microfluidic chips are really electronic pneumatic hybrids. I think that's a useful maybe way to think about them. That presents some interesting challenges. In particular, I think we have good techniques for detecting errors and attacks in the electronic part up here. There's decades of research into that kind of thing, but maybe less so in the pneumatic part. So maybe this part down here is a little underexplored and needs to be addressed. So the attempted answer to that we were playing with at UC Riverside was, can we take error detection techniques from the electronics world and possibly implement them in the pneumatic side of things so that this half of the control chain here could be monitored actively for errors or attacks. So we're trying this. This is really kind of half of a finished story, which is still work in progress. But I'll tell you the first one of these ideas that we've been playing with today. This is a parity bit generator, a really conventional electrical engineering approach to error detection. So I'm a chemist by training. Lord knows I'm not qualified to explain this to a room with a bunch of electrical engineers. But in the off chance that anybody hasn't encountered this, I'll talk you through it very briefly. We have data, like 4 digital lines here. Those are like the signal going to my on-chip valves, ultimately. Those could be true or false. For example, 1's for true, 0's for falses. If those go down into this network of little XORs, exclusive ORs, we can step through it. So 1 XOR 0 is a 1, that's a 1, that's a 0. And so this calculated our parity bit for these inputs to be a 0. So that will be passed along with the 4 original bits. That then is sent via some sort of communication, usually a wire, but in this example I'm going to show you how we'd send it with pneumatics to the chip. That's sent to a receiver, which receives those 4 bits plus the parity bit information. Those go in there. And then it does the same basic computation, uses XORs to calculate what the parity bit should be. It then uses a final XOR to confirm that those two are the same, and there was no error in this example. So yay, the 4 bits of information were passed successfully, and no attack or failure occurred. To show you an example of a failure, if this bit here erroneously were received not as a 1 but as a 0, when we go through the parity checking, we find these are not equal to each other. The error bit output is a 1. All right? So that's parity bit 101, I guess, for you. So that was what we settled on, and we had the idea, can we implement this, take advantage of this in the microfluidic world? And so there's this picture again. Doing the part of it here, generating the parity bit, that part's easy. That would be done in silicon, in the computer, in LabVIEW, or whatever the hardware is. So in sending the data to my valves of the state that I need them to be in, I'll send that data. In the computer, I'll calculate the expected value of the parity bit. Those then get transduced into the pneumatic domain by my solenoid valves, and those get sent to my microfluidic valves, which do their usual job. Nothing new yet here. But in parallel, we'll also also branch those pneumatic lines off and send them into an on-chip pneumatic parity checker, shown here conceptually, that will on the fly detect whether any errors were encountered in the propagation of the signal from here all the way through to the microfluidic valves. All right? So we need a technology for making that little on-chip pneumatic XOR-based parity bit checker, and so we had a technology like that kind of at our ready here. We call these monolithic membrane valves. I developed these about 15 years ago at this point. Lordy, time flies. And so this is how they work. These were sort of the first microfluidic valves suitable for large-scale use in rigid materials and microfluidic devices like glass microfluidic devices. So they consist of a displacement chamber etched in the pneumatic wafer, we'll call it here, across from a featureless PDMS rubber membrane. And on the top here, a discontinuity in the fluid channel where the valving is occurring. When we stack these things together, you get a valve, and you can have hundreds or thousands of these on any one microfluidic chip pretty easily. So from cross-section, this shows you very briefly how they work. You see that the valves are normally closed. The fluid can come in here, but when there's pressure or no connection on this little input here, the fluid can't get through from here to here, and that valve is closed. But if we apply a pneumatic vacuum down here, this bends the membrane down. Fluid can flow from point A to point B, and the valve is open. And that's it. And so we use these for a bunch of things. Here's a little video of 3 of them in a row make a pump. Pretty straightforward example of a little microfluidic valve. What it can do there, it's pumping air and blowing bubbles. And so they were used in a bunch of different things. I'll highlight a few of them where they were used in their conventional ways. If you haven't seen these sorts of things, then I'll tell you how we do computing with them next. They were used in the first device that automated all the steps involved in Sanger sequencing of DNA that ended up being commercialized in this instrument by a company Intogenics. They were part of a process that demonstrated the first Darwinian evolution on a microfluidic chip to evolve a novel ribozyme. Pretty cool stuff. And a really cool one here. See, I found a way to put Allison's work in here at my talk. We were talking earlier. They were used in an instrument for looking for life on Mars, as a matter of fact, too. So that's pretty cool. All right, that's not the part I want to tell you about. The point that I want to tell you about is the finding that we can use these for logic circuits. And now hopefully implementing some detection of errors or attacks. So the idea of this sort of came where we looked at the valves early on and said, well, they were designed to control the flow of liquid in a biochip kind of way, liquid in and liquid out. But we, on a lark one day, asked the question, could they control air pressure or vacuum? The same air pressure or vacuum that operates them, could we also send that into the input, and would it go through to the output? Then it's the same sort of connection on all 3 of these. This starts to look a little bit more like a transistor, right? Which is interesting. So we tried that and went through and developed a set of 6 little rules about the combinations of pressure and vacuum on each of the inputs and the controls. I won't dwell on these, but they basically make 6 little design rules that are the design rules for really any valve-based logic circuits that you'd be interested in making. And so we made a bunch of those. Just to show you probably one of the more complex ones, this is 130-some microfluidic valves wired together into 8 adders. So it's capable of adding any 2 8-bit numbers. Here you can see it in the process of adding these 2 numbers together to get that sum there. And so it's the world's slowest adder. It takes about 3 or 4 seconds for the carry information to propagate all the way around. The open valves light up because the membrane stretches and they become concave and they reflect a little bit of light, if you're wondering why they're lighting up like that. But so this is, I think, one of the more complex computations that's been performed using air, not electricity. So they're versatile. They'd be good enough to make this little parity bit checker if we want to. So we're in the process of doing that, and so I'm going to show you what that chip looks like. This is an XOR made out of these valves. Vacuum is 1 or true, a pressure or atmospheric pressure is a 0 or false. And so I can kind of real quick talk you through how this thing works if you're interested. Here are my 2 inputs. There's the output. So in the case where there's no vacuum in either one of these, it doesn't open either of these valves, so vacuum from up there doesn't make it through to here, and no vacuum goes out there. So that's why 0 XOR 0 is 0. If these are both true, or there's vacuum on both of these, it does open these valves, which sends vacuum down, but it also opens these little bleed valves here, which sends that vacuum, if you will, out to the atmosphere. I guess that's backwards. The atmosphere is actually coming into the vacuum, but you get the idea. It's a little awkward. The atmosphere is like the ground plane in these circuits. So when those are open, it derails that vacuum out in these side directions, and again, neither of these valves open. So that's why 1 XOR 1 is 0. That's the exclusive part of the exclusive OR. But in the other 2 cases, when that but not that, or that but not that, has a vacuum going into it. Then this opens, but it doesn't get derailed out there, so it opens that or that, and the vacuum gets through. Does that make sense in a nutshell? So that's how the XOR works. It takes 6 valves to make one pneumatic XOR doing this. Here's a video of the thing in progress, in operation. So that's one of the early gates we made, and it works pretty well. So it's cycling through the 4 possible inputs there. So to turn this into the parity bit checker that I was describing, you just need a bunch of XORs, right? So this is the rough design of what we're working with. So I showed you that. Here's a paste job of 1, 2, 3, 4, 5 of them. It's got, in this example, 1, 2, 3, 4, 5 working inputs that would be the pneumatic signal that's intended to control the valves, the normal valves, the working valves, the valves that are doing your biochip work, plus a 6th input that's the result. It's another input, and that's the result of the parity bit that the computer that's controlling this whole thing calculated. That all gets fed into this mess here, and then there's my outputs, all right? So that's good enough. So we're in the process of testing that chip right now. I wanted to show you the way you would apply it to an actual biochip application. This little example here, which might be clearer to see over there too, shows 5 valves hooked together to be a serial diluter circuit here. So we see a fluid inlet here, these 5 valves, and a fluid outlet over there. And so I'll step you through a quick 3 or 4 step typical application for these biochips. Then I'll show you how you could use the pneumatic logic and the parity bit checker to impart error checking to the operation of this chip. So in the first phase of this thing, you can see these 3 valves, A, C, and E, opening and closing in a sort of a peristaltic rippling fashion. Can you see the shading here? It's a bit hard to see in this animation. Maybe you see it over there. So we'll spend some time in phase 1, which loads the main channel here with fluid. Then in phase 2, we'll load the side channel with fluid, actuating valves A, B, D, and E in that little peristaltic rolling pattern that you can see in the animation there. In phase 3, we'll actuate B, D, and C in a rolling manner that sends fluid around and around in a circuit here to mix the things. And then in phase 4, we will dispense the fluid, the mixture that's now in the main channel here, out to the exit. Okay? So a pretty simple microfluidic operation, but I wanted to show you kind of when you code these things in LabVIEW or something and actually control that, you realize how complex even something as simple as this little chip can be. This is the state of all 5 of those pneumatic lines, valves A through valve E, right at every step in the 4-phase, several step cycle that I just showed you. We repeat each one of these several times. There's actually more individual steps than this, but these are the unique steps, and we'll repeat over and over each of these. So you can see these little patterns to the open and closed valves. And so an error in any one of these would make it not work, right? And so that's where I think this sort of thing becomes interesting. You realize how much information goes into controlling these things, and how, even a small attack or a small error occurring would render the operation of this not doing what you wanted it to do. So to integrate what you saw up to this point with the parity bit checker, the pneumatic logic, to that chip, it would amount to just putting upstream of this. There's my 1, 2, 3, 4 valve, 5 valve serial diluter circuit. So then the control lines are coming from the solenoid valves, from the electrical side of the world. They go through first to the biology, which is this is where the chemistry or the biology is happening in my serial diluter. And then they go on to the rest of the chip, which is error checking, to make sure that the message that was sent pneumatically from the control line is correct. And we'll have a single output here that will put out a vacuum if there was an error, and nothing if there wasn't an error. All right? And so armed with that, that would calculate a parity bit. Here I've manually calculated all the parity bits. So these are the expected values for those. They just happen to alternate like a zebra there because of the nature of this pattern. And so any deviation from these expected values of the parity bits at every step in that process there would be an indication of a mistake, an error, or a communication failure, the like. So we're working on that. So to wrap up showing off this little chip, there's this chip here that we're playing with here has 5 working or fluidic valves that are actually doing the real biochemistry, whatever, and 30 logic valves, which is sort of weird and silly. There's a lot of real estate over here, you could argue, that's being dedicated to the logical, the computing side of these things compared to what's actually doing the chemistry or the biology. But I'd still kind of defend this. I think that it provides valuable information. I'll show you examples of what you can do with that information here at the end. But also just sort of the nature of microfabrication, right? Making a chip go from this size to this size generally isn't doubling the cost of the chip, right? The economies of printing techniques and photolithography and things mean that we can make make our chip a little bigger and integrate some logic onto it for not a huge cost. So I think that for some applications, having logic valves as well as chemistry biology valves and the logic valves then supporting the operation of the chip can be quite helpful, especially if it means we can reduce or eliminate the amount of off-chip computer equipment required to operate these too, which is an interesting application of these ideas too. So to wrap up, I wanted to comment and think about what could you do with the pneumatic error signal in practical real-world cases that's coming out of this, right? So you remember this will send out a pressure or a vacuum when an error is occurring here based on the parity check bit analysis and nothing otherwise. Well, one thing you could do with it is have it notify the operator. And I put this whistle here as it's kind of tongue-in-cheek, but you literally could hook a whistle up to this, right? I love the parallels and the weirdness compared with like programming a conventional electronic kind of thing and have it, beep an error out versus programming a pneumatic computer of sorts. And in the case of alerting the operator for a pneumatic computer, a whistle literally is the bell that it would play. And so we actually have, for another project, not this, we're working on ways to generate sound in microfluidic chips using airflow. And so you could literally couple those two things together and have your chip go when there's a problem. That's the least interesting thing you could do with this, but I still think it's worth mentioning. What else could you do with it? Well, the output of this could go through a pressure sensor, a transducer, back to the electronic world, right? And there, it's easy relatively for me to have another line, a digital read in this case, or whatever, or analog read, that's confirming the value of this. So that at every step in the operation of that process that I was showing you, after all, I have an electronic feedback that's basically telling me, diagnosing the health of the entire pneumatic system here, the chip. That sounds nice and probably useful. What else could it do? It could control, we could use the vacuum from this to act on the fluid, the biology, the chemistry, whatever's happening here. So we could recover gracefully from errors, right? So for example, I can easily, in theory, set this up so that if an error occurs, it'll apply the vacuum from there to the fluid line here and suck out all the contents of the chip and send it to waste, right? So in that case, if I don't know the nature of the error, but if the chip is smart enough to realize, ah, crap, an error occurred, then I'm going to fail gracefully, aspirate away to waste all of the offending questionable material now because we know it's not trustworthy because an error occurred, and alert the user with my whistle and basically have program into the operation of this a graceful shutdown. I think that's good. And then perhaps most interestingly, this is a pneumatic signal just like all these other pneumatic signals, and we've demonstrated not just XORs but all the other gates too. And so this could be feedback to control the other valves. This could literally, when it detects an error, it could literally reboot the system. It could cause a process in here that causes it to gracefully start over and recover from the error and hopefully get it right the next time. All of that in pneumatics, all of the logic of that recovery being covered in the pneumatics of the chip, not in the electronics that are hooked up to it. And so if you don't think that's realistic, I think it might be not too far-fetched. This is work from my colleague Elliot Hui down the road at UC Irvine. This is a finite state machine that he made using these valve principles. And so this is literally a computer for all intents and purposes that runs on compressed air or vacuum, and it's able to do incredibly complicated things. So integrating error recovery into this state machine would be a relatively small addition to what he's already accomplished, but it could impart resistance to attack and errors in novel ways. So, and then finally, final slide, I mentioned that these ideas of pneumatic logic circuits for detecting errors aren't limited to acting on biochips or microfluidic biochemistry devices. Think of anything that has a pneumatic signal or signals to it that operates, like these weird robots that Boston Dynamics makes and we watch the YouTube videos of, or these sorts of things, or exoskeletons. Any system that has a lot of pneumatic lines to it could, in principle, have on board a little bit of a pneumatic error detection circuit using these principles that would provide feedback on the state of the system and if it's being affected by an attack. All right, so with that, I'll shut up and acknowledge some funding sources and, yeah, and answer any questions y'all have. Thank you.
To the pressure change.
Of what? The valves or?
The operation of it.
Right, yeah, good question. You need, like any good transistor-like structure, you need a certain, above a certain threshold to open the valve, and then when the pressure drops below that threshold, it will close automatically. And so... especially
when you propagate will be more and more resistant.
I got you. So you're saying when one valve's controlling another, which is controlling another, the signal would appear to deteriorate. But that's exactly right. And so to address, we found that, and to address that, we made amplifier circuits that basically use a fresh vacuum coming in. It's like, it's basically ripping off an idea that MOSFET circuits use. You always have a vacuum line on top here in one channel, and you can use an amplifier, buffer amplifier, to turn a small magnitude vacuum into a full magnitude vacuum, which can then propagate further downstream. Yeah.
So to follow on the question that was asked by Cliff, the pressure, if an attacker tampers with the pressure source, can you tell that? How easy is it to tell that there is an intruder or some malicious intent?
I hadn't thought of that one. That's a great one, but I guess the challenge would be, could you make either a valve-based circuit or some sort of structure that, I guess to accomplish that, if you have a structure that just behaves differently depending on the level of vacuum or pressure differential going into it, I'd have to think about what that structure would look like, but if you could implement that, then the output of that could be another thing that goes into the XOR, right? That detects the state of the system. Yeah, good question.
So you also were assuming a single failure.
Yeah, a single bit failure, right? Right, which, as you know, with the parity, if I fail 2 bits, the parity bit looks good again. Yep, that's right.
So that bits you can play with 2 pressure
Right.
sources.
And that's where I guess in practice, folks only use the parity bit in situations where the likelihood of failure is low, and if there is a failure, it's likely going to be a single bit, not multiples. But then to address multi-bits, of course, there's many other, I'm just mentioning the parity bit here, but there's many other checksum kind of techniques that in principle could be implemented with a bit more complexity, in this sort of thing. Yeah, but good question. I've seen yours.
This is probably inherent in the architecture. I missed it, but so there's some arrival time for the inputs to your XOR.
Yeah.
And then some output.
Yeah.
How do you decide when to sample that? How is that happening so you're not getting glitches and things aren't arriving?
It's hard, because you saw from the adder the fact that the carry information took 2 or 3 seconds to propagate. So we would always laugh and say these are limited to the speed of sound in terms of the speed of that. In fact, they're much slower than the speed of sound. But in principle, that's the fastest that this information could propagate. So you're right. It takes some trial and error. We don't have this down to a science enough where we have rigorous design rules that can address that. Another thing that is like what you mentioned but different is latching. It's quite easy to get a vacuum trapped in a section of this chip that's difficult to remove. And so sometimes we'll have to add additional valves that are a reset valve. They just vent certain parts of the pneumatic system that typically store a vacuum when you don't want them. That can be useful because that's 1 bit of stored information, whether or not a vacuum is stored in an area or not. So we made latching valves that way. But it's bad because it adds, further difficulty in designing these things. Does that answer your question?
Yeah.
Yeah. It's basically I'm just saying it's hard. Yeah.
How big are these things? How many gates can you put them on a
Yeah, the valve's a millimeter or so in size. So that 8-bit adder is a 4-inch wafer, I think it was. I didn't try hard to make that smaller. Elliott Way at Irvine is making them quite a bit smaller. They're a little bigger than electronic circuits, though. Full disclosure.
I think this question was Scott.
Oh, yeah.
So, you mentioned bit latching.
Yeah.
So obviously, a lot of encryption incorporates a random process.
Yeah.
So is there an unstable state you can get where?
Yeah. Well, great question. Oh boy.
You might want that.
Unstable. I need to, great question. So is this a random number generator or something on it? Yeah, I like it. If you put 3 knots in and make a what's that called?
Ring oscillator.
Ring oscillator, thank you. It will self-oscillate. And so then, I think anything you could build out of structures like that could be.
I think what Scott is saying, it's a buff, right? You can have a buffer for these chips. Physically unclonable function.
I see.
Isn't it?
Puff. I learned an acronym. Okay.
Pneumatic puffs. I think.
Pneumatic puffs. It's an actual puff.
Random, obviously, bit strings is an important part of encryption. So
Yeah.
whether you could use to do that.
Yeah,
I like that.
Every chip will have its own different property, right? When you
Yeah.
do ring oscillators.
Yeah. Yeah.
The other puff, silicon.
Okay.
Thank you for a very interesting talk. So I guess I'm not very sure about how the automated recovery that you mentioned works. Because what you're doing is actually you're comparing the parity of the electronic domain with the output of the solenoid valves. I mean, you can definitely detect error, you can definitely alert, you can definitely suck. Yes, I understand that part, but how are you going to recover from that error? That's not clear to me, because if the error is on the solenoid valves, then it's a hardware problem, right?
Right.
Not really,
Okay. Okay, good. Well, I think I see. Well, so just to think of a particular failure, say the solenoid valve sticks open or closed. That's happened to me. You know, I know for sure that's a real error. Exactly. You wouldn't. The software side of it wouldn't know that, right? You're saying, and I'd agree with that. The electronic side of it would have no way of knowing that. But I guess using these things, in that case, I would want to use that pressure sensor, where the output of my whole parity bit comparison, that pneumatic signal, gets sensed in turn and sent back to the silicon side, to the computer side. In that case, right? You'd see if you agree or not. But I think in that case, that would be that would cause a parity bit failure because the solenoid valve was not in the state that you intended it. The computer didn't know about that, but the pneumatics did. And the pneumatics, by doing this calculation, sent that information back to the computer through a sensor. That's my guess. Yeah.
So I think it's interesting that you're applying all these digital kind of concepts of how to do error correction and detection.
Cool.
I'm just wondering, is there a more kind of fundamental way of doing the same thing in the medium itself without translating all the way back into the digital?
In the medium, you mean the biological medium?
Or the pneumatic medium in terms of what you have?
I see. So instead of ripping off electronic digital ideas and implementing them in the pneumatic, are there other...
In other words, like kind of the whole system in order to do the same kind of thing that you're trying to without having to convert it to digital first.
Yeah.
And
I think so. It kind of brings to mind, I think, Krish, some of your work where you try the different states of flow through a system and measure flow resistances and things and can infer from certain, am I right, if I misrepresent your work, can infer from certain resistances and things, intrinsic things about the fluid system, the health of it, the state of it, if things are failing at a particular location. So yeah, I think that's definitely worth pursuing, and I think some of that work's being done.
So I think the key is to map your ones and zeros to some measurable quantities in this domain. So, for example, pressure, right? Union 1 is a pressure of some value.
Yeah.
Union 0 is some other pressure value. Something like that you have to do.
Yeah.
I have a follow-up question on the one that Doug. Sorry, did I?
Oh no, I think there's
your train of thought?
no. It's just that I think in general when we look at a lot of this kind of work, right, which a lot of researchers seems to, especially from a security standpoint, want to move everything into digital.
Yeah.
And I think in some respects you might be losing a lot of promise in your vertical medium, the analog side.
Yeah.
Right, just because you're making the shift. So I'm just trying to get a better understanding of what are we using.
That's a great point, right? That we we have decades and decades of digital computing. It's the lens through which we look at this stuff, and you're totally right. Yeah. That being said, because we have so much good material from the digital world, I think it's worthwhile to do both. What you were saying, Yeah.
So going back to Doug's question about when do you observe? So there's a problem of both min time and max time, because it takes some time for the pressure to proper. There's a channel RC time constant.
Yeah.
But also air can leak through the PDMS. So if you wait too long, you lose it.
Yep.
So unlike in electronic, right, you can't run it too slow. You have to get it. So there's a window. That's very important.
Yeah.
That has implications on attackers' modalities. The attack's surface. If the attacker can somehow affect the flow rate, the pressure amount, the time you sample, you may get incorrect results.
Right. It manifests itself as like the wrong volume being pumped or the wrong mixture, occurring. Or that's a good point.
So the analogy for what a lot of research is sometimes you take your car to a gas or whatever repair station, and you can measure air pressures at different locations.
Right.
Like they looked at these different signature of doing well or not.
Yeah.
Converting to digital.
Yeah.
So analog side channels would be whatever that would be an analog side channel.
Yeah.
For example, here if you have PDMS channel, the air is going to leak out constantly, and that's a side channel, right? So I can easily tell that there is flow in this
It's a literal side channel, potentially.
So,
Yeah. Cool.
Well, this is rather common question, actually. I attended one of the talks by Elliot Hui.
Yeah.
And actually he said, if you have a chip like this small, but behind this chip you need such a huge instrument to run this chip. So it's not really portable.
It's not a lab on a chip, it's a lab around a chip, or so people say, which is true.
Right. So he said, if you can make such a pneumatic-based computer, then you can really make it small and portable.
Yeah.
And I think that's his point.
Exactly. And that's why, and I alluded to that briefly, but that is